Dear students, study of computers is complex, and yet the more a student delves into it, more engrossed he becomes and is fascinated by the immense scope that it unfolds in terms of current and future applications. At the same time, the aura of mystique that computers generate in the initial stages of study is replaced by an increasing sense of enlightenment. This film on computerized system development, implementation and control is yet another step towards such an enlightenment. It aims in specific to acquaint you with the basic tools required for developing, implementing and controlling computerized systems.
Every system development effort, whether it is batch or online, consists of 7 phases. Phase 1 is involved with the activity of problem definition. Phase 2 with feasibility study. Phase 3 with system analysis. Phase 4 with system design. Phase 5 with system development. Phase 6 with system implementation. And Phase 7 is involved with system maintenance and review. Let us examine each activity in detail before we proceed further. Coming to Phase 1, that is problem definition, the following points are salient: statement of scope of the problem, statement of objectives and performance criteria. Before a system analyst comes to grip with the problem, it is important for him to understand the nature of the problem and the resources available to solve it completely. In the second phase, feasibility study, the feasibility of designing the computerized system should be examined from all angles, a few of which are economic, technical, legal, political, social, employee acceptance, and manpower requirements. In the next phase, system analysis, the following points should be kept in mind by a system analyst: data flow in the system, editing of input data, processing to be done on the input data, decisions to be made regarding the outcome of processing done on the data, and design of suitable output formats. The fourth phase of system design is an interesting and challenging stage. It basically covers alternative solutions analysis, hardware specifications, plan for implementation, user friendliness of the system, test plans, formal system test procedures, security audit, and operating procedures. The next phase of system development involves actual programming as per user requirements, compilation, and testing of the programs. The sixth phase of system implementation involves proper system documentation, training of the user staff, and actual implementation on the hardware system. The last phase in the system development life cycle, system maintenance and review, is an exercise in assessing any possible change in user needs, refining and tuning the system to changed user needs, providing revised documentation if needed, and decision to change over to an entirely new system if required.
A cardinal rule to be remembered in system analysis and design is that an error detected earlier in the system life cycle is easier and cheaper to cope with than an error detected later. This can also be represented in a graphical form. We need not look far to find the reason for this. It is quite simply due to the fact that more effort, cost and time will be required to undo the faulty decisions and actions taken at the earlier stages. If we were to analyze the effort distribution at different times in the system life cycle, then we would be possibly looking at a pie chart. As is clear from this pie chart, the maximum time, approximately half of the system lifetime, is taken up in maintenance, while the other significant portion, testing and debugging, takes up approximately 1/4 of the system lifetime. This is because testing, debugging and maintenance are important to get accurate results from the computerized system and therefore need more attention. At this stage, let us see what are the various problems one may come across during the system life cycle. These may differ from one system to another, but the ones more likely to arise are response time. This should be fast enough to cater to the needs of the system. Scope of failure of the system. Due to power failure, bugs in the system or mechanical faults in the hardware should be minimized, otherwise fatal system breakdowns may occur. A certain degree of self-correction and review methods. These should be inbuilt in the system, especially for online maintenance, like in the case of rocket launching systems, offline maintenance downtime in case of batch systems like shared accounting, and online systems like railway ticket bookings should also be taken into account. Online system design. This should take into account the capabilities of the computer system, like the number of tasks or programs it can handle at a time, or number of terminals which can be attached to it. Security. Access to the system by unauthorized persons should be minimized by means of security features like password. The worst problem in ill-designed systems is the ripple effect, where fixing a bug or bugs in one part of the system produces a bug or bugs in some other part or parts of the system. To overcome this problem, we have to have a framework for structured systems analysis and design. While doing a structured design exercise, it should be kept in mind that there are independent modules with least of coupling between them. Such a system is the most changeable without the ripple effect coming into play. To build a structured program, we use structured coding and build programs out of a few standard logical structures, each with one entry and one exit. Any program can be built using certain techniques to achieve this purpose. Structured programming tools comprise of sequence with no control transfer, binary decision if then else, and loops perform until. An important process to decide the structure of data files in a system is normalization. This is especially important if a database is used and is the theory behind relational databases. It aims at the simplest form of data representation, which is in effect a two-dimensional sequential file or table.
Let us now examine a few more tools required for systems analysis and design. DFD or data flow diagram, flow charting, tight English, structured English, decision table, decision tree, and hypercharts. Now let us talk about these tools individually. The first one is DFD or data flow diagram. This is a logical model of the system under study at any level of detail. Before we come to the details of this model, let us examine the symbols that are used for this purpose. A square is used for source or destination of data. A rounded rectangle is used for a process which transforms flows of data. An open-ended rectangle is used for storage of data. And an arrow is used for flow of data. This is, for example, how we can represent a bookseller's business details. Here, process orders is the process used to process the data. Customers is the source and destination of data, and book data and customer data are the stores of data used for processing. We can expand the process orders process as follows. Here, the verify order is valid and assemble requisition to publisher processes can be exploded to any level of detail. The next tool, flow charting, has the following main symbols to represent the flow of logic of a program. It should be noted, however, that the flow charting template does not apply to the system flow charting. An example of a program flow charting could be taken for an arrangement of two numbers in descending order. Now, tight English and structured English put verbal descriptions in a logical structure which removes logical ambiguities. An example of tight English is as follows. As is seen in this chart, tight English uses a numbering scheme to simplify indentation. Statement 5.1 checks whether the credit limit has been exceeded. Statement 5.1.1 specifies what has to be done if the credit limit has been exceeded. Statement 5.1.2 specifies what is to be done if the credit limit has not been exceeded, and so on. Coming to structured English provides the keywords to structure process specification logic as a block-structured language, while leaving some freedom for describing the activities and data used in the process as with block-structured languages. Process specification logic consists of a combination of sequences of one or more imperative sentences with decision and repetition constructs. An imperative sentence usually consists of an imperative verb followed by the contents of one or more data stores on which the verb operates. For example, add person salary to total salary. Structured English uses certain key words to group imperative sentences and define decision branches and iterations. These keywords are assign, repeat, if, end, until, then, case, while, else, of, do, and for. An example of structured English is as follows. Let us now take a look at decision table. Although structured English and tight English can describe most processes, such process descriptions can become clumsy if we try to specify a process that selects one of a possible set of actions using a set of complex rules, especially if it is necessary to repeat a decision or to do the same process more than once to retain the logic structure. For example, consider the following structured English specification. The logic of this structured English example becomes more clear if we construct a decision table. It should be noted that tight English is similar to structured English, and decision trees use the same ideas as decision tables. An example of a decision tree for a trade account is as follows. We shall now discuss the last tool for system analysis and design shown earlier, namely hypo or hierarchical input processing output chart. This system is described by the components known as hierarchy chart, which shows the hierarchical decomposition of functions, and input process output charts. An input process output chart is made up of three components: the inputs to the function, the outputs from the function, and the transformation performed by the function. There is one input process output chart for each function. Let us consider the following example. To prepare an order, we determine availability, look up prices, and prepare a shipping document. Here the input process to be done on the input and the output desired is shown.
After review, testing, and evaluation of the completed design, we come to the project implementation portion of the system analysis and design exercise. For this, the following points shown in a chart form will be useful. If in a system, the old system does not exist, the question of replacement of old system does not arise. However, if the old system exists, one may cut off the old system and install the new system abruptly, or cut over from the old system to the new system by segments, or operate in parallel and then cut over. Coming to the steps in implementation, they are shown in this chart on system implementation: the plan, space and layout, manpower and organization of MIS, training for operators and users, hardware equipment installations, program development, design of forms and files, and testing and changeover. It may be noted that these steps are not mutually exclusive, but may overlap. Control of an ongoing system generally involves the following: system audit, debugging, and changing the system to suit the user's changed needs. So friends, as you may have gathered from this film on computerized systems development, its implementation and control, 7 phases are involved, from the definition of the problem to its design, development, implementation, and its maintenance. This elaborate exercise is undertaken so that the errors, if any, may be detected as earlier on in a system life cycle as possible. The system design as such must be well framed, for the ill-designed systems have many pitfalls. Keeping these aspects into consideration and with the help of the tools, an effective computerized system can be evolved.